Get ready to introduce our speaker here. And it's always a great time to introduce one of our own, one of our former students who's returning. So Vivek Rao, who earned his PhD, so it's Dr. Rao, earned that in 2018. But prior to that, he also got his master's degree here. And then after getting his PhD, he became a postdoctoral fellow at Oak Ridge National Labs, and then has now been hired as a full-time engineer at Oak Ridge. As you can tell from his title, computational fluid dynamics is a big part of what he does. And so without any further ado, I'm going to go ahead and turn it over to Dr. Rao. Thank you.
Thanks, Dr. Newkirk. I have a fondness for Rollo. I spent 8 years there in grad school. I was loyal to the Chem department, starting in Schrenk Hall, and the Bertelsmeyer building didn't even exist back then. And my first year and a half of the master's degree was focused on radiolytic synthesis of nanoparticles for carbon nanotubes, and that was right here in Dr. Castaño's lab. We had a novel method invented by Jessica Rojas, and I believe she's at Virginia Commonwealth right now. And I had such a fun time in Dr. Castaño's lab, late nights running experiments, and I thought, who would ever want to run a simulation? This is the real deal. If you don't run an experiment, it's not really research, is what I used to think. And then I got a reality check a couple of years later when I realized what my PhD project was with Dr. Smith in the chemical engineering department. And Dr. Smith also is a chemical engineer. This is Joseph Smith, but he also has had his leg in nuclear engineering for a long time. He was at Idaho National Laboratory. Dr. Castaño, I believe, was also at Oak Ridge. And I started to see why being at a national lab is important, why being open to new ideas is important, because that's where real research happens. And I have not run an experiment in the past 5 years. I'm exclusively a desk jockey running simulations. So we'll look at some of that today. So a big good afternoon to everybody. We're going to look at applied CFD. So we're not going to really look at equations or what source terms we're putting in different applications. This is more about the colorful fluid dynamics on the computational end, but we'll see what the value of using these tools is in today's industry. Okay. A brief outline for today is a brief introduction to ORNL, Oak Ridge National Laboratory, some unique capabilities that we have here, why computational fluid dynamics is a hot topic or a buzzword or something you're going to see in a graduate program or even at an undergraduate level nowadays, and how you can actually benefit by applying this to true process engineering with some examples of projects here. Last but most importantly, how you could get involved in the years to come with a national lab, if not Oak Ridge National Lab. So this spread here shows you the real layout of Oak Ridge National Laboratory. The structures you see in the gray boxes in this second row are called directorates. And we have a directorate structure. We report to a single laboratory director through the executive committee at the top. So we sit over here in the Fusion and Fission Energy and Science Directorate. If you were wondering who worked here, it was people in the Fusion Energy Division and Nuclear Energy and Fuel Cycle Division. So being nuclear engineers must be a very familiar term to you. But that does not restrict our collaborations to be within the directorate. We collaborate within our divisions, between our divisions. We call them sibling organizations. And all across. We have people working with isotopes, with national security, with biological and environmental sciences. I've worked on marine power, on building technologies, on neutrons. I mean, name it. It's wonderful. You get to collaborate and interact with people with such varied experiences. And that's really how you see the value of research. And what you thought was a good opportunity 2 years ago only gets better with time to come. Something that might be of interest to the A&E department is really the last bucket over here. We have the exascale computing project. Exascale is basically pushing the frontiers of computing with exascale computations, with floating point operations or flops that are in the exascale. There was recently a publication using a code called NEC 5000, which is enabled on GPUs and demonstrated at a reactor scale. This is definitely recommended reading if you really want to see the power of computing, the power of doing neutronics, fluid dynamics, and anything else in between to design a nuclear reactor. This was a multi-laboratory effort, and there's also a project called the Exascale Computing Project, which most of these organizations are participants of. We have the Neutron Upgrades Project, and then of course we have US ITER, and US ITER is the American leg of ITER, and there's Google can tell you a lot of information on that. We'll look at some ITER-like systems today, and that'll be in one of our showcases. So with fusion and fission, this is just a brief description of our directorate here, which may be of interest to everybody there. Our fusion energy division has 8 groups split between 2 sections. The first section is burning plasma foundations, focuses on plasma theory, diagnostics, and tokamak physics. Our second section is fusion, nuclear science, technology, and engineering. Also has 4 groups, but they look at blanket and fuel cycles, fusion technology, fusion engineering, and remote systems. You'll be happy to know there are many Rolla grads between these 2 sections. And in the nuclear energy and fuel cycle division, I sit in the advanced reactor engineering and development section in the thermal hydraulics group. We have about 24 groups spread across 5 sections here. We also have a radiation safety information computing center, which is RSEC down here. So just within our directorate and the division, we interact with people from various backgrounds, physicists, chemists, engineers of all sorts and kinds and shapes and sizes of experience, technicians, computing experts, modeling experts, physical testing experts, name it. It's a beautiful medley of all things that you thought were possible. So let's look at some unique capabilities within our directorate. This is in the fusion and fission space. There are tens of unique facilities spread across the national lab, as there are with any national lab in that case. But Oak Ridge National Lab has a history going back to the 30s and 40s, to the graphite reactor. If you watched Oppenheimer, you get a better sense of that. Within our directorate, FFESD, this is one of the first unique facilities that came up about 7 or 8 years ago. This was a molten salt test loop, which used a Flynac salt, which you may be familiar with. And this was really a push from both the molten salt reactor world as well as concentrated solar power, because molten salt is one of the leading candidates for energy storage system, where you can actually store the energy and then release it depending on the grid demand. And that's where the figure on the right is really from what's been touted by the US Department of Energy, CSP's concentrated solar power. And this is essentially having circumferential arrays of solar panels, which are focused onto a central collector, which looks a little like something from Raiders of the Lost Ark. But it's quite funny. There's a project that's in development. I'm not sure which stage of execution it is, but this is out in Nevada in the desert, where they've got a CSP facility up and running. But I'm not up to date on the facility, but it gives you a good visual of what such a facility looks like. And molten salt's a leading candidate. If you look at the specs, this is just a test facility, but in a real system, you're going to be dealing with larger volumes of salt, greater heat loads, and more complex marriage of materials, so to speak. One of the high temperature materials here is Inconel 600 and silicon carbide. One thing you'll notice is we're operating at atmospheric pressure. Now, this is one of the touted benefits over light water reactors, which have to be pressurized. And this is a big safety relief by operating at atmospheric pressure. This test loop was in operation. As you can see here, we have a heat map from a few years ago. And over the past few years, a chloride test loop has been put into operation. This facility is called FASTER, and it stands for the Facility to Alleviate Salt Technology Risks. Faster is supposed to push the bounds of thermal testing to about 700 or 725 degrees Celsius, and is really intended for corrosion studies. If you look at this table on the right, this is the instrumentation suite that we have to enable corrosion studies. And of course, it enables auxiliary equipment in the instrumentation suite. But there's really a lot you can do, and this is really set up to have vendors in the nuclear space come and try out novel materials in a molten salt environment. So if you can get a baseline for corrosion performance, that could really inform the choice of materials, and that's where you take it in to study the effect of irradiation, the effect of pressure, the effect of temperature, and all those amazing things combined to see if you can push the bounds of generating clean nuclear power. So how have these facilities been put together, really? You know, you do back of the envelope calculations, you have Excel sheet calculations, you have analytical correlations for pipe flow, for heat exchanger sizing, all of that's great. When you put all those 220 pieces together, can you really tell what the performance is supposed to be through an Excel sheet? Or can you predict turbulence inside a pump? Can you predict the damage on impeller blades inside a molten salt pump? Well, that's why we start at the component scale, and this is where CFD starts to rear its head in. Equipment sizing, equipment design, and component scale design in general are expedited using computational fluid dynamics. What is computational fluid dynamics? It's really a fancy word for a code that gives you a quick solution, but gives you a realistic solution, and the solution is an engineering approximation. It's basically garbage in, garbage out, until you can actually prove that what you've done is reflecting reality. That's your validation process. If you take an analytical correlation for pipe flow and you say, well, you know, I have laminar flow in a pipe, I should see a parabolic velocity profile. Great. If your code doesn't give you a parabolic velocity profile for laminar flow in a pipe, you should not be using that code to design equipment. So there's a hierarchy and best practice guidelines that have been put forth by various agencies such as the NRC and by NASA. There are various studies, that have been put forth specific to various engineering problems. But really, a lot of these successes, be it molten salt or being the material plasma exposure experiment, are really a combination of both failures and successes from various disciplines where CFD has been applied and proven to be a valuable tool. Now, the real applicability only comes from validated benchmark exercises. So MPEX, or the Material Plasma Exposure Experiment, is a unique setup that's coming up at Oak Ridge National Lab. MPEX really is trying to understand the challenges of ITER-like fusion reactors. The fusion reactor concepts usually focus on the toroidal design or the tokamak design, but understanding conditions that are replicated in the ITER diverter can be simplified by linearizing the plasma device. So MPEX here is called a linear plasma device, and it didn't just happen overnight. There were a lot of analytical calculations, many engineering approximations, computational tools that were put together. What you see here is really a snapshot from a CAD model. CAD model again was put together using smaller pieces such as flanges and bolts and nuts all together, trying to follow the constraints of the ASME boiler and pressure vessel code and other regulatory requirements that have been put forth by other engineering successes and failures. So when developing a facility, you really have to start small and start looking at individual effects before you look at integrated effects. MPEX itself came from proto-MPEX, which was the prototype of MPEX. And the main objective here was to see if the source system could demonstrate the production of plasma with certain specifications. The electron densities had to be in the range of 4 to 6 into 10 to the power of 19 per cubic meter. And electron heating and ion heating had to produce values of up to about 25 EV. So having proof of this principle and concept put into practice was what allowed MPEX to evolve. This is a very detailed plasma-based design, and I'm not a plasma physicist, but some recommended reading and high-quality visuals are available on the ITER tokamak website. One of those links that will be very useful is the diverter, because that explains what the ITER relevant diverter condition is, and that's really the crux of this entire project. So what's really our motivation? Why are we chasing these problems? Why are we trying to get molten salt to flow at 725 C? Why are we trying to get a linear plasma device to understand how what plasma material interactions really are? Where does that get us? Well, we're trying to go away from fossil fuels. This is something that's very obvious and is the need of the moment. Various offices of the US Department of Energy, such as we abbreviate a lot of these offices, but Energy Efficiency and Renewable Energy is EERE. EERE touts is pushing for hybrid energy systems. The Advanced Manufacturing and Industrial Decarbonization Office is pushing for devices that enable low carbon or no carbon technologies. And essentially designing newer materials that have longer life cycles, are lightweighted, are compact, are resilient to different environments, and can enable those technologies which make low carbon electricity a possibility. Something that's not obvious. Why decarbonize the maritime industry? Maritime industry really is, what is it? Shipping containers out of which dinosaurs are accidentally released. If you think of Jurassic Park, well, not really. Your 2-day shipping on Amazon Prime is probably, using land-based transportation. But things that come from overseas, car components, batteries, things that are non-manufactured in this country or in any country that have to be imported or exported, rely on shipping routes. And those are some staggering statistics right there quoted by the US Department of Energy. So there's a general need to decarbonize life and the engineering sector altogether. Chemicals manufacturing, plastics manufacturing, reducing the use of single-use plastics. That's really the push for materials that are not at the mercy of single use, and materials that are more efficient in both their upstream life cycle of production as well as their downstream recycling habitat. So as long as they don't end up in a landfill and have a future life, those are all enabling technologies. So let's really get into the computational aspect of how we're using these tools to push into real life applications. So a lot of these technologies like molten salt or, nuclear fusion at this stage today, many of them can't stand alone to support life. We're using them as auxiliary energy generation systems. Some countries produce a lot of nuclear power. Some countries produce next to no nuclear power. Some produce none. And so it's really an integrated effort. So hybrid energy systems started off being very much dependent on fossil power, but then adding in smaller pieces of cleaner technologies. Now we're trying to flip the story and say, well, these are going to be the driving forces. So some of our top choices are bioenergy, solar power, which are nuclear adjacent, and nuclear power itself. One of the key issues where we've been using computer-aided engineering, or CAE, is another abbreviation you may have heard of is CAD, which is computer-aided design. They're all interchangeable. Is really to address some key issues under each bucket. If it's nuclear processes, these are familiar, fission and fusion are just putting it simply, but these are the main applications where you'd use computational tools. Bio and solar power have some key issues which all upstream and downstream vendors tend to focus on. What's the need of the day? If we think of our previous slide, sustainable transportation, hybrid energy systems, clean vehicles, decarbonizing the maritime industry. This is being pushed for by offices at the Department of Energy exclusively. This is the Bioenergy Technology Office, the Hydrogen Fuel, which is probably now the Hydrogen and Fuel Cell Technologies Office, and the Vehicles Transportation Office. What is common to all of them? They all suffer from a lack of understanding of true thermal transport processes. Broad strokes, they can be summarized in some of these buckets. Multi-phase interactions, you have air-water systems, you have oil and water systems, you have particle and liquid systems, particle gas systems. This is where true reaction engineering comes into play. Flow regime dynamism, you can have static cooling, you can have active cooling, forced convection, free convection, call it what you want. When you use liquid metals in different nuclear technologies, whether it's to cool or in a secondary purpose, under the influence of temperature, there could be flow stratification. You may have heard of thermal striping. That's where it comes down to this bucket. Reacting flows and phase change, if you use refrigerants or waste heat recovery systems, if you're trying to oxidize, if you're trying to reduce samples, all those things fall under reacting flows. That's just putting things simply. There are various catalytic processes. If you drive a diesel vehicle, you probably have a catalytic converter to purify the exhaust system. Designing those exhaust systems requires a good knowledge of phase change and reacting flows. And of course, last but not least is material behavior, because if your material can't survive the process, you don't have a process. Once you surmount an understanding of these thermal transfer processes, you realize that you're wasting a lot of energy. So waste heat recovery is now the need of the day to enable sustainable transportation. And this has given rise to something called balance of plant, where if you could trap any waste heat and reintegrate it into the process, into the power generation process, you could make a process more efficient. You could change the underlying correlations in textbooks that tell you how to use reflux streams from different thermal systems. So where computational tools are really coming in is to design reduced order models, which can give you plug and play approaches to your power generation or equipment-based systems. Experiments to give you a validation or benchmark baseline saying, yes, the computational tool you're using is set in scientific bedrock. V and V is verification and validation, which is putting those two together. Benchmarks are to tell you or provide you a range of applicability for your computational tools. Materials response is, of course, getting a thorough understanding of what can cage your process and give you a reliability and improve operation and maintenance costs. And of course, LCA and life cycle analysis, techno-economic feasibility, these are all just implicitly required in any equipment or process design at this stage. Of course, once you succeed at all those things, you can commercialize your technology. And no technology is ever going to be completely risk-free. It's about understanding in as much detail as possible and providing a minimal uncertainty quantification so that those technologies can succeed at a commercial scale. So if you look at our successes and failures from nuclear power generation, if you take broad examples, the flow regime, transport phenomena, fluid structure interaction, thermal hydraulics, these are just broad, familiar terms, but when you put them all together, you get a multi-physics tool. Modeling and simulation. The models usually will give you a basis to execute those physics in a mathematical form, and the simulation actually provides an implementation on the computational environment. So this is how other sectors, energy sectors, can benefit from successes in nuclear power, because computational tools have been used a lot more in the nuclear industry. Let's jump into some examples. The spallation neutron source at Oak Ridge National Lab. This is an accelerator facility. We have two target stations, the first and the second target station. First target station over here uses a liquid mercury cooled stainless steel target and is impinged by a proton beam, which is accelerated through this facility. Upon impingement, the process of spallation occurs inside liquid mercury. And the neutrons that are produced in the process are what are used by other scientists and a plethora of users to test their novel materials, their samples in a neutron-rich facility. If you go back to the link here, if you simply Google SNS ORNL, you could even take a virtual tour through the facility and walk past the accelerator and anything else that you might want to see. Very exciting. A study was done using computational fluid dynamics about 20 years ago, and it made some assumptions that were not necessarily qualified, but it was the best guess study. This was in the year 2019 through 2020, when I got to work on this and do a full computational model of the core vessel at the SNS. So this is a quick CAD view of the facility. It's a combination of stainless steel and carbon steel structures implemented in computational space. This is the extracted flow path inside the core vessel. So it's not just a bunch of tubes or just a couple of plana that give you cooling. It's an intricate structure. And, you can really use pipe flow correlations over here. You could use them on localized spaces, but if you look at the flow path, going from 1 to 2, 2 to 3, 3 to 4, and 5, it's a complex structure. And so you may have laminar flow in some places, turbulent in some others. You may have backflow, you may have stagnation, so many unanswered questions. Really, we wanted to basically get a thermal map of the core vessel using computational fluid dynamics. So we had a neutronics team that gave us a text file with an XYZ map of the power density. And we were able to map that into our CFD code and look at how much power was deposited through direct energy deposition by the proton beam in each of those components. That's the beauty of CAD. You can segregate components specifically and demarcate boundaries and contacts so that you can quantify how much heat is being transferred between any two pairs of bodies or interfaces. And you can see some of the bodies receive up to about 16, 17 kilowatts of energy, whereas some of them receive less than 1 because they're distant. So their assumptions have to be qualified, and this is how you can qualify them and say, well, we don't need to consider this because it's receiving less than 1 watt. But if you say that right off the bat, there's no basis. So using this, we were able to map the hydraulics in the system, the hydrodynamics, understand what the pressure drop was in the system, look at 2 scenarios. One was a nominal operation, and the other one was reduced thermal conductivity of the solids. We assumed a 20% reduction in thermal conductivity due to the use of irradiated materials. So one's the best case scenario and one's the worst case scenario. And so if you have reduced thermal conductivity, you see a higher accumulation of heat in the system or in some of the structures. So you could see some localized temperature increases. It may not be much, but maybe a couple of degrees, but it's something that you need to quantify before you say it isn't much or make an assumption. Here we're able to look at the spread of the proton beam in terms of temperature and look at what the heating profile was in various diagnostic and viewports in the core vessel. Similarly, we were able to look at the shielding, at the temperature profiles under different conditions, the 2 main structures through which the proton beam is supposed to pass through and deposit the greatest amounts of energy. And it took us 960 CPU cores and about 72 hours per simulation to get through this. Our next example is also at the spallation neutron source, and this was the actual target system. Now, there have been several target designs over the past few years, but this is a very complex system. The beam that impinges it hits it at 60 hertz. And it's, well, of course, cooled by liquid mercury. The nominal beam was operated at 1 giga-electron volt, and part of the proton power upgrade project was to push that to 1.3 giga-electron volt. So you're increasing the heat load on the system. And the design was to see if we operate the pumps at the same nominal speeds of so many RPM, do we need to change the flow rate? Do we need to change the design of the target? Several strategies to improve thermal mixing the targets have already been explored. These are some really detailed studies. Definitely recommend reading them. To improve gas liquid mixing inside by helium gas injection, and to actually orient the jet to the nose of the target during flow recirculation. So where exactly is the target? Is it just a standalone device? Well, the target sits over here in the mercury process loop. And you can see it's a flow process loop, just like the molten salt loop or any other flow loop. There's a heat exchanger, there's a pump, there's the actual target, and the beam impinges it over there by the nose of the target. What that looks like? Well, this was the predecessor design called the blue target. And you had 2 annular inlets, which would combine at the nose of the target. This is where the beam would impinge, and you would have a common outflow return. How the design evolved? Well, they removed the gas injection system and introduced a swirl bubbler and removed the diverter baffle on the inside. What that looks like, we'll see on the next slide. So there have been different issues over the past few years, and the target has failed a few times. And so this is basically our lessons learned approach to redesigning the target and making it more efficient, improving the life cycle of the target. This is a front view comparison looking down the nose of the target. So you can see the design isn't simple. There are ribs here to enable mixing. You have the nose of the target, and this is a symmetry view, so this is only half the target design. But there are simple flow modifications that could streamline the flow better, remove an actual physical structure, and still not see any deterioration in mixing. Now, what that actually looks like, we were able to use computational fluid dynamics to look at this. Should have a video that's playing. Anyway, this is inflow coming down into the swirl bubbler up here on the left. And you can see the jets separating out. And then you see the formation of eddies. Now, this uses a time averaged model. So you don't really see the decay of the eddies in detail that would be desired. What you do see is a very diffuse pattern that impinges the nose of the target. And you see this U-turn, essentially, this green zone where you have a fairly uniform velocity. And that goes all the way down the return segment. What may not be beneficial is this large stratification and velocity. What you want to see is a smooth diffuse pattern going through the wall. Some of this is unavoidable because you do need the flow to reverse. But one of the implicit design features of the target is you have mixing both along the nose, the circumference of the target, as well as along the lateral span of the target. So now this is something that you expect in theory, but when you actually look at it, you're able to discern the flow patterns upstream and downstream of, say, the swirl bubbler, which is situated up here. And when you induce that rotation in the flow, what you see coming down the nose of the target is this very uniform lateral profile. So as time goes by, the flow stabilizes and the peak value reduces, so you see a more uniform pattern. And this is more during startup where you see a point location with a high velocity and much less. And this is something that's common to most nuclear applications. When you think of spacer grids and nuclear reactors, if you think of steam generators, usually do see a flow perturbation at certain locations, but a fairly diffuse field otherwise. But here, just by changing the heat load and getting a new heat deposition from the neutronics team as a simple table, we were able to import that into software and look at the spread of the beam for different scenarios. This again is your nominal beam. If you look at the high temperature zone, that's likely where the beam would impinge on the target. If you were to overfocus the beam, the spread of the beam would reduce, and you would see a slightly higher temperature. This is a greater energy concentration in the same unit volume. And if you were to underfocus the beam, you'd see a greater spread, and you can see it tapers off towards the top of the nose. And so you'd have a larger span for heat removal, but because there's a greater area of incidence, you have a slightly lower temperature as the peak value. So looking at profiles that way, you could look at both the wetted walls of the heat exchanger as well as the exterior walls of not the heat exchanger, of the target. And that helps you quantify heat exchange in each case. So these beams, if you look at the flow profiles and temperature profiles, you can see some qualitative behavior because this is where the flow reverses. But until heat transfer is actually significant, this is very deceptive because the temperature is quite uniform and you can't really get any flow information. But when you look around, you can see that this is the direction of flow because that's where the temperature tracks in line with flow profiles. So we were able to run, these are just a few snapshots from a detailed study. We were also able to look at the effect of gas injection without actually modeling gas flowing through it. One of the established cases is to simply insulate the top surface of the target because that's where you would see the mixed jet of liquid mercury turn around and impinge. So basically by saying, let's just say there's no heat transfer here, we're emulating a gas layer that's stratified at the top. And so if that qualifies your limiting condition, that's good enough for the time being. We were able to quantify how much energy was deposited in the solid volume, how much was direct energy deposited in the mercury, and how much heat was then, of course, the 60% that's deposited has to be removed by the mercury to maintain a favorable operating temperature. That helped us design the target and qualify it for the proton power upgrade project. This is from MPEX. This is just a quick, brief example. This is the ICH system up here in this figure, lies over here. This is an ion cyclotron heating system. that's used to as a part of the cumulative heating system of the plasma in MPEG. Now, this again adds to the rescue because this is really telling you what the detailed design is, and this is used in finite element analysis for electromagnetics and thermoelectric calculations. We decouple that part of the calculation and simply take the part that's incident in the thermal circuit, the part that's incident to the plasma. The plasma operates at near vacuum conditions, but the exterior boundary of the system is cooled by water at about 220 psi. So once again, if this is where MPEX conditions came from, they came from proto-MPEX. And you're seeing in proto-MPEX, they saw heat fluxes as high as 14 megawatts per square meter. And these are in the regions of low electron densities. If you consider about 80 kilowatts of heat incident in the system being conveyed through the ICH launcher, you can see the setup over here. You know, we have flanges that were of a certain well-conducting material. Then we have the quartz window, a Faraday shield, and we have several other layers here which haven't been revealed. But we have water flow inside the system coming in through the flanges and then along the annulus. There's a transition flange in between, which we'll see in a little more detail. But it was a very intricate design that could not just be purchased off the shelf and built. And this is where computational tools have led the way. So if you look at our plano, this is the water inflow region, and then you have the solid region. But by depositing energy in the middle, you can look at the conduction pathway, the convection pathway, and heat transfer within the water. Now, there are design constraints for MPEX. There are certain temperature requirements for outflow from a system. You have to ensure that you're well below boiling temperature, so you have a design margin. All of that put together, we're able to map the heat deposited by the plasma from the science team. Once again, tabulated, given to us, and implemented in the CFD code, and we could use that as our boundary condition to calculate what the temperature was across. And so we did have to do several material replacements to find a material capable of surviving that temperature, which also fell within the cost requirements. So going back to that previous calculation of putting all the pieces of the puzzle together, you have to have technoeconomics, you have to have life cycle, you have to have design, you have to have materials response, everything qualify and be in agreement for a system to go into practice. If you were to take a simple, convective heat transfer formula and say, well, what's my heat transfer coefficient in the ICH launcher? Well, there isn't a single answer. If you look down here, you can see the coefficient's high where the water comes in and then it decreases along the length. As you remove more heat, there's less of a gradient. There's less of a temperature gradient. That's something you could say, but you wouldn't be able to predict these high temperature zones for heat transfer coefficient in the transition flange. So here it did serve its purpose. It was to take flow that's become fairly uniform and isn't mixing much anymore, perturb it through a transition angle, and basically have several smaller jets come out, and you would improve the heat transfer in the second pipe. So these are some of our success stories, and of course these are just detailed flow maps looking inside the system, and that way we could pinpoint, extract these maps of pressure, of temperature, of velocity, etc., and pass them on to the finite element team, which would use the pressure and hydraulic loads, which is these, where you could decouple the restart of things like turbulent boundary layers, and inform them in their thermomechanical design. So this was run by a thermomechanical analyst in ANSYS in a different package, but all we needed was an Excel sheet to go between the two codes. And if you were to use the same set of software from usually the same vendor, you can do a lot of this in real time. As you're computing a flow solution, you're able to map it over to your thermomechanical software and run that calculation. This is just another example of calibrating a molten salt pump. This is nuclear relevant. I'll go fairly quick. What we tested here is just a simple example. We have molten salt here in red, and we have a purge gas at the top, which is in blue. They're conserved by volume fractions, so the sum of the fractions is equal to 1. You see at 0.5, which is this green-yellow layer, you have the interface between the two. And we said, well, if you were to fill one to about 20 inches, what would the flow look like? And if you filled one to about 22 inches, what would the flow look like? So we were trying to do some flow rate calculation at the impeller, which is located down here. But the animations tell you what the flow patterns look like. And if you're seeing breakage in the flow, are we seeing uniform Do we see a film that forms along the tube? Do we just see this eddy that falls off and the flow separates? We had other inferences, but this is just an example for visual aid. How we can quickly design things like spacer grids. If you just take a tube bundle, the classic 3x3 or 5x5 sub-channel experiment, we've been looking at these minimal surface designs. They're periodic in three-dimensional space. They offer very low pressure drop across the span, and they're very flexible in computational tools. You can simply put in an equation, change the value, and you get a different set of void spaces along the spacer grid, which currently doesn't exist in most designs like the Westinghouse design. You have uniform spacing all around the fuel rod. But here, if you look closely, you have a small flow acceleration gap right next to the southern boundary of the fuel rod. To the northwest and northeast, you have a larger void space. To the southwest and southeast, you have an intermediate void space. So you're never really giving the flow a chance to stabilize. You're constantly inducing swirl along the spacer grid at a very low pressure drop. So these are some studies we're running currently on a different design, and you could apply it to heat exchangers. It could be a tube sheet for a steam generator. It could be for spacer grid design. It's very flexible. This is an example from a past project. I'll skip through this in the interest of time. This is what's called a direct contact heat exchanger. It's a heat exchanger without internal walls separating the fluids. It's recommended for use when you have immiscible or weakly miscible fluids. What we have here is a waste stream of hot water that's injected through the top. And we have pentane, which is sparred through the bottom as droplets into the water. The goal here was to essentially inject the droplets of pentane so that into a heated pool of water where you had fresh water coming in, the pentane would start to vaporize and form a steady height in the heat exchanger beyond which everything would be vapor. You'd have a jet of water coming down the middle and a steady active height, which is characteristic of direct contact heat exchangers. So we looked at different configurations of nozzles, different inlet flow rates, different inflow temperatures of waste heat of water to design the system. This is a fun exercise in CFD and in phase change. So if we look here, come back to this slide. Really quick, we have a high velocity jet of water coming down from the nozzle above. Comes in about 318 Kelvin. So this was snapped at 318, but we looked at the range of temperatures going up to about 95 degrees Celsius. If you look at the volume fraction, we have water, which is this jet coming down here, and you see this abrupt stop because this is where the vaporization begins. And the water diffuses to the bottom, settles due to density separation, and you see pentane vapor form and it floods the reactor. What you see on the right here is essentially plots of ISO surfaces, ISO or constant value surfaces. We fixed the volume fraction and we were able to track the scarring or the penetration of water going into the jet of pentane coming in. So for different nozzle configurations, you could look at the dispersion of the droplet going into the water. If you were to look at an animation, you could see initial chaotic droplet formation, and then you see pentane gas settle at the top, water settle at the bottom, and the temperature being tracked, going all the way down to the bottom of the reactor for 180 seconds. Then we do a grid sensitivity to study to see, well, how fine does the grid need to be for us to track this active height? And so we ran a validation exercise after that. And then we were able to get to a steady operating height as we wanted to. So you have a jet of water coming down, you can see trickling through. This active length is what remains steady. And you can see this, it took us about close to 900 seconds to reach that steady state. 900 seconds is about 15 minutes, or exactly 15 minutes. So you can see a steady stream of pentane being barged in. You see a steady evaporation height, and then you only see vapor above. So this was a success. Now the company, Eaton Corporation, wanted us to design one on our own based on a validation study. So we started here. We had a lot of chaotic vaporization, and so we said, this is great and all, but this is too chaotic. We can't have this system up here. So we gradually moved on to a separate set of designs, which all looked idealistic, until you have something like this, where you have no active height or no active front for vaporization. It's chaos. This looks like a Van Gogh painting because it's a vortex street. So is this favorable? Probably no, because the vent and the drain were placed right above each other, and you had this big stagnation zone with water at one end and pentane in the other. We had vortex shedding, or the von Karman street, or at some extent of the street. It's a fun thing you see in paintings and ink blots and other places like that. And essentially, we have liquid going through the vapor vent. So this was a no-go. But simple modifications were possible. So, this was our final design. And if you look at the first animation, this is just two jets of hot water coming in from the left, pentane from the bottom, and you have this turbulent evaporation over here, but you reach a steady height. And we said, well, let's calm down this upstream chamber. So we introduced some baffles, and that gave us some unfavorable stratification in the first reactor. But once that stabilizes, you have a continuous flow above and a calm interface at the front. That was published with the American Society of Mechanical Engineers in the Power Conference. We got just a few more minutes, so I'll skip through a little quicker. This is a project which involves smelting. Your conventional lead acid car batteries get broken down into scraps and fed into a furnace. Furnace is powered by natural gas burners. And what happens is you have combustion reactions here, as you see on the left, classic four-step Jones-Linson mechanism for hydrocarbon combustion. And the heat from that combustion is what sustains endothermic smelting. Smelting now is essentially solid decomposition from a larger solid to a smaller solid with the release of a gas. You have CO2, SO2, and H2O that are released primarily. And then some of the lead that just comes in as elemental lead melts. We have to simulate combustion, solid decomposition, heat transfer between every pair of phases, and melting all in a single simulation. So I will not get far into detail over here, but these are just some representative snapshots. We're able to simulate the flame coming into the furnace. This grayed out outline that you see is a particle bed that was loaded in using particle dynamic simulations. Here's some fun animations of loading the furnace. This is coupling particulate dynamics with gas flow or Illyrian fluid flow dynamics. And we're able to do heat transfer to the particles and then from the particles back to the gases. It's called two-way coupling. But here we're able to look at the spread of different, well, of course, basic parameters such as the temperature and the time step and the particle size, because it's a fraction of what the gases move at. But we're able to look at how the composition of the reactant coming in changed, which ones react quickly, slowly, and the formation of a melt front of liquid lead in the reactor. This was published with TMS, that's the Journal of the Minerals, Metals, and Materials Society. This is a case from an ARPA-E project. ARPA is the Advanced Research Projects Agency. E is for energy. There are other arms of ARPA. One of the programs, this is from a few years ago, was called Integrate, but it was to basically clean up natural gas technologies. So our team was called Nectar, I believe, which is the second abbreviation. One thing you get used to working at a national lab is abbreviations. We love them. Some of the heat exchangers we designed, this is a basic shell and tube heat exchanger with coils that could handle very high pressure drops and give you high rates of heat transfer. It gave you favorable flow distribution in the shell side, so to speak. We evolved from those designs to more of the periodic minimal surface designs, and we were able to hit very good numbers on the kilowatt per cubic meter scale. So if you had a heat exchanger for certain sizing, you could use these numbers to scale up and down. We looked at the effect of the angular frequency inside the periodic surfaces on the heat transfer rate. In inches, what you see here is the wall thickness. So this is a parametric sweep. And essentially, we have a performance map for our heat exchangers. We're able to look at, these are just pairs of designs, but if you were to look at the slope, if you change the frequency, you would get an increment from, say, 2 pi to 3 pi. You would go from, this would be your multiplication factor. So you could do the same thing with wall thickness, with the number of unit cells in the heat exchanger. This is a very fun study. And if you see that the maximum pressure drop was less than 5 psi. For reference, 1 atmosphere is 14.7. So this is a very acceptable engineering design. We're able to take these numbers, plug them into reliability analysis, FEA's finite element analysis. but we were able to quantify the stresses from the hydraulic and thermal loads on the system and look at the deformation inside each of those solid structures. From there, we evolved to an actual heat exchanger rig, and this was a design which we closed the project out with. So it was a cross-flow heat exchanger using high temperature inflow at 619 C. The cold fluid was at 267 C, which is still pretty hot. But we were able to design this flange and gasket system with an entry manifold. And we ended up 3D printing the core of the heat exchanger. That's what it really looks like. This is the minimal surface design. Some profiles on the inside. In CAD space, that's what it looks like. Mathematically, that's what it looked like. Streamlines of flow going into the cross flow. You can color them by temperature, and you get a lot of insight. You see a lot of back mixing over here. You see some jet formation down here. These are once again varied for wall thickness and the number of unit cells. You can see the void spaces here are larger than the ones over here because the void space here is essentially there are 1.5 times the number of unit cells in there, to put it simply. Once again, we developed a pressure map, a reliability map. It was very much in line with the program. And then this is further optimization that we're still working on. Could talk for days about this stuff. We did some aerodynamic analysis on the core of the heat exchanger, looked at pushing it up to Reynolds numbers of 125,000 for aerospace applications. And we were looking at the jet stream that was formed in the wake of the design. You could use this as a static mixer to induce turbulence in phase separation. You could look at the acceleration of flow, how much bypass flow there is in the heat exchangers. The last of these things, this is just a fun thing to look at. A simple math equation which gives us the core of the heat exchanger. When you parameterize a lot of the key variables, you can actually change the compression ratio, the expansion ratio. Especially if you had high-speed flow, you could decelerate it at a very low pressure drop. And there are ways that we would love to show you how to do this. So in the last few minutes, I just want to talk about how you can get involved with us. How many of you are undergraduates? Okay, that's a good number. We have a ton of programs to get involved with. So you may be aware of most of these, and I've done my best to Dr. Castano and Dr. Schlegel whenever I get a chance. It's usually, by the time I find out, the deadlines are really too close. But you can simply Google ORNL student programs, and this page will pop up. It's publicly available. There are some that are hosted exclusively by the lab, as with every other lab. Some of them are hosted by the Department of Energy at the lab. So a variety of options. Many of the undergraduate programs are restricted to U.S. persons, which is a citizen or legal permanent resident. We have some graduate programs as well, fewer, for the same reason. One of them is restricted to citizens and LPRs. The Office of Science graduate student research program is open to more than U.S. citizens. We have several other ORNL programs, and we also have a faculty program. This is something I did not know about, so I will forward this along to faculty, but this is a good way to get involved. And lastly, I'd like to thank my division at ORNL, the Fusion Energy Division, for the opportunity to work on MPEX and some other projects. All the heat exchanger work we did was with the Building Equipment Research and Integration Center. The Computer and Data Environment for Sciences, CADES, is now home to the Oak Ridge Leadership Computing Facility, OLCF, where our supercomputers are hosted. Most of our CFD codes are not GPU ready yet, but the supercomputers themselves are in the top 3 supercomputers in the world right now. That order shifts every few months, but we have Frontier coming online for collaborative use pretty soon. Most of our CFD work, or my CFD work, I should say, was done with Siemens products or CD Adapco products, and they've been very helpful, and we get competitive pricing from them. Of course, the Chemie and NE departments are where I spent all my time from 2010 to 2018. So last but not least, everything's, you're always in progress. No design's ever completely done. And Dilbert is always a gentle reminder of that. So thank you all for your time. Can't believe that was 100 slides, but we raced through some of them. I'll take any questions. I'm willing to stay late if you have more to discuss.
Okay, let's have to our.
Yeah, no, it was a lot of information.
Yeah, we're like over the time, so if you have like a quick question, anybody? I have one. Why does the spallation neutron source have a reactive pressure vessel? Or a pressure vessel?
The core vessel is part of the lower outer reflector plug. It's more of a structure that's formed in between, and they call it the core vessel. But it's
Okay.
really the LORP, the lower outer reflector plug.
Okay, but it's not a pressure vessel. Okay, got it.
No, yeah, it's not a pressurized system. There is heavy water cooling,
I saw
and that operates under a separate loop. But this is just sort of the flow path that's evacuated through those structures.
Okay. Let's take our speaker one more time. Thank you very much.
Thank you.
I will be asking you about that faculty visiting, program.
Sure. Yeah. Yeah. We'll stay in touch.
Definitely go and check for the students. Okay?
Yeah, I was wondering if there's anywhere that we can just view the list of opportunities they had up on the screen.
Yeah, I could email them to the faculty. Yeah.
Okay. Yeah, if you send it to me, I'll be happy to share. Just email me and I normally will post it on campus, but nobody's raised their own campus doing one person.
Yeah, and now's a good time to apply.
Yeah. Okay.
All right.
Okay, thank you very much.
Thank you.